All right, welcome everyone. This is CS110, Introduction to Computer Science. I'm Ruben Meshan, I'll be leading the course. And not too long ago, I was a student, like you, except I wasn't a computer science major, I was actually studying biology. I wanted to become a doctor. Somehow the idea of opening someone up and digging in there and messing around with their organs seemed appealing to me. My problem, though, was that I was also interested in other things, right? I was interested in finance. I was always reading the news. I was interested in politics and different things. And the idea that I would spend sort of the rest of my life just doing that one thing, as interesting as that might be, I began to panic. What was I to do? I was interested in so many things. How can I choose just one? And so I went through a series of changing my major. I think I changed my major to international relations at one point. And then I realized, okay, that's great, but I also like engineering and I also like these other things. And eventually, after speaking with a lot of people way smarter than me, I noticed one fundamental fact, which is that computers are everywhere, right? Software systems exist in every domain. Absolutely every domain, whether you're in the medical field or whether you're in banking, computers are everywhere. Computers run the world. And so what I realized is if I can learn how to program, if I can learn how to manipulate computers, then maybe, just maybe, I may be able to move around and try different things, and maybe work in the medical field for a little bit, and then maybe work in finance, and then maybe work in aerospace, and so on. And so I did that thinking, this is a great idea. And then I went to my first class, which was Introduction to Programming Using C++. Raise your hand if you know C++. I am incredibly impressed. Awesome. I did not know C++. In fact, I had never done any programming at all. And just like what you saw here, the class that I was in was full of people that had been programming for a long time. There were people who knew Java, there were people who knew C++, there were people who had done assembly. If you don't know what I'm talking about, there's just lots of programming languages, it doesn't matter. Okay, so people knew what they were talking about. I barely knew how to email. It was bad. And as the course went on, I felt like the dumbest person in the room. It was really difficult. The idea of functions, the idea of variables, of scoping and looping and recursion, all these things that eventually all of you will understand, were very foreign to me. I didn't know what to do. And for a long time, I struggled. It was very difficult. But what I did is I decided that, look, this is what I have chosen to major in. In order for me to have the freedom to work in any industry, I have to do this. And so I forced myself to learn it. And I spent literally all day, like I would wake up in the morning, go to the lab, which was basically a room full of computers, start programming, go to class, come back to the lab, go eat, come back to the lab, blah, 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 go home, repeat the next day. And I would do this every day. And eventually, after many, many weeks of me struggling, it began to make sense to me. Okay, it began to stick. And that's when, after a while, I realized, hey, this is pretty cool. I can build things from nothing. When using a computer, I'm no longer limited by the applications that were built by others. If there's a game I want to play that doesn't exist, I can just make it. If there's an application or a tool that I want to use that doesn't exist yet, I can build it. That's pretty cool, right? And in fact, that's exactly, have you guys heard of Amazon.com? Okay, the guy from Amazon.com, he went home one night and decided, hey, we should build like an online store. And he himself sat down and built the original version of Amazon.com in one night. In one night, one programmer sat down and built Amazon.com, the very basic version, okay, just the fundamentals. And that was enough for him to start putting it out there and start testing it out and see if people like it and they're going to use it. And eventually, yes, it picked up pace and so on. He hired more engineers, and it grew to be the giant that it is today. Other examples include Zuckerberg's Facebook. He was sitting around his dorm room. Why not? Why don't I sit? I wish there was a nice platform where people could communicate. I'm always in my room. I'm a nerd. I'm a programmer. I want to talk to girls. let me build a website where they will come and I can see their pictures and they can see my pictures and I can poke them or whatever. Okay, that stuff, right? So he did it, and there you go. And then you got Facebook. So the cool part about this is once you understand computer science, once you have this gift, this ability to manipulate and control computers, you can leverage this to do really big things. The fact that you are in Armenia, or whether you're in Yerevan or somewhere completely different, as long as you have access to the internet, you can build applications and deliver them across the world, globally, and make lots of people happy and yourself rich, by the way. Remember that the more value you provide, the happier people will be to give you money. Okay. So what this means is every time as you're using various applications, if you see something is missing, gee, I wish this existed, you can just build it. You don't need money. All you need is your time. You have the skills as a programmer. You just need the time. Sit there, build it, deploy it, see what happens. When I was a student, there was a major barrier to entry in the startup community. You needed some money in order to start. Why? You needed a computer. Specifically, the kind of computer that serves web pages, okay? A server, if you will. These servers needed to be maintained, provisioned. They needed to be made sure you have to keep them cool. You need to back up your data in case something goes wrong. What happens if they shut off the electricity? Does the website go out, right? Maintaining a live server is an incredibly difficult and expensive task. Today, we have cloud providers like Amazon, Google, IBM has a clouding system, where you can just go, log in, give them your credit card, and then basically choose the kind of computer you want to use, how much memory you want, how much processing you want, and then basically rent it. And you're only paying for what you're using. And initially, if you're not using it too heavily, it's actually not expensive at all. That means this barrier to entry, this barrier to getting into business, is no longer there. And by the way, to do this kind of business, a business degree will not help you. An engineering degree will. Zuckerberg was an engineer. The guys from Google were engineers. All the big shots began by building it themselves. Engineers are the ones that run the world, not the business people. That's my pitch. Okay, so I thought, okay, this is pretty cool. I can start, manipulating computers and having them do what I want. Now I want to solve problems. And this class is exactly about that. It's about solving problems. Now, if you think about it, every time you want to solve a problem, you must first understand the problem, right? You really have to understand it well. You have to understand every little detail. You have to understand the things that affect the problem. You have to understand the variables, the parts of the problem that can change. And taking all of this into account, you then use your engineering skills, your engineering prowess, your understanding of computation to deliver value, to deliver a solution. So again, the first thing we have to do before we start trying to solve a problem is to understand it. So the question is, how does a computer store information? That's the first thing. So it turns out that the computer has these little things called transistors, okay? Transistors are like little switches. They can be in one of two states. They can either be in an on mode or an off mode, okay? So what I'd like to do is use this lamp to represent a transistor. Ta-da! Okay. Thank you, thank you. So this is a transistor. It has two states, right? An on state and an off state. With me so far? Okay. Now, suppose we wanted to represent a number, okay? How could we do that using one of these transistors, right? Well, we have two states, right? Two modes, an off mode and an on mode, right? So one thing we could do is, okay, we have numbers, 0, 1, 2, 3, whatever. Well, maybe if it's off, why don't we call that a 0? And if it's on, well, the next number would be a 1, right? Okay, so using one transistor, which has two states, an on and an off, we could represent two things, which in this case, as a number, we can represent a 0, off, or 1, on. With me so far? Now suppose we want to represent a larger number. Well, if you think about it, we only have two states. So we actually can't represent a larger number if that's all we have, if all we have is two things. So what we need is more of these, more transistors, more of these things. So, ta-da! I have more. Okay, so you might say, okay, fine. If they're off, then they're 0. Okay, I think that's intuitive, right? Okay, if one of them is on, that represents a 1. Okay, so off was 0, on is, okay. Then you might think, okay, well in that case, if you have 2, then you have 1 being on and 1 being on. 1 plus 1 is 2. So this could represent 2. And actually, if you did this, it would be fine. You could do this. This is correct. The problem is, what would you need if you needed to represent the number 3? 3 of them, right? If you needed to represent 1,000,000, how many of these would you need? 1,000,000. You would have to turn on 1,000,000 of these, right? That doesn't scale very well. Imagine if you wanted to represent 10 billion. You would need 10 billion transistors just to represent that one number. That doesn't scale very well as far as hardware, right? So let's do something more intelligent. Consider this. With these 2 lamps, how many states can we represent? We have the off mode, right? That's 1. One of them being on would be another state, right? Another combination, if you will. Another one being on would be a third combination, right? And then lastly, we have our fourth combination. It's interesting. So with 1 transistor, we can represent 2, but with 2, we have 4 possible states, 4 possible combinations that we can represent. So if with 2, we could represent 0 and 1, with 2 lamps, with 4 possible states, we could represent a 0, a 1, a 2, and a 3. 4 possible states, 0, 1, 2, 3. With me so far? Interesting. Now suppose I want to keep going. So far we can only represent up until including 3, right? 4 possible states, 0, 1, 2, 3. Well, what happens if I want to do 5 or 6 or 7? What do I do? Add another lamp or add another transistor. Very good. Here we go. I don't have any more. Just, okay. All right. Okay, so interesting. So I wonder how many states we can represent now. 8. So let's make sure that we're correct with our hypothesis. So this, all of them off, would be 1, right? That's a 2, another combination. 3, 4, 5, 6, 7. Right, and okay. Wait, no. I meant to do that. No. Exactly, right. 8 possible combinations. Interesting. So with 1, we can represent 2 numbers. With 2, we can represent 4 numbers. With 3, we can represent 8 numbers. You guys notice a pattern? Exactly. So it's 2 to the power of the number of transistors. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Excuse me. Okay, very cool. Question. You said 8 states, right? So this represents a 0 or 1. This represents a 0 or a 1. Okay. So what is this? No. What value do you think this represents right now? Only one of the lights is on, right? Right? Sorry. What value does this represent? 1 light. 1. 2. 3. 4. 7. Very good. Now question. We said there are 8 possible states. And yet when all of them are on, we have 7, not 8. Why? Very cool. Exactly. Because we need to account for 0. It's 0 through 7, not 1 through 8. In fact, one of the things that you'll notice as we move forward with this curriculum is you'll see that very often we will begin counting at 0 rather than 1. So computer scientists always go 0, 1, 2, 3. They don't do 1, 2, 3. Okay? So just FYI. Cool. Okay, so a little bit of theory. So binary, the word binary, which I'm sure you've heard somewhere, bi means 2. Okay? So binary means you can represent using 2 things, 2 values, right? On or off, 0 or 1. Black and white, standing or sitting. You get the idea, right? One of 2 states. The numbers that you're used to, however, decimals, deca is 10, right? So decimals use base 10. It's a base 10 system. Everything is 10 at a time, right? Binary uses base 2, base 2. So let's look at how this works. Suppose we want to represent the number 123, or 123. Okay, so in regular decimals that we know, we have the ones place, the tens place, and the hundreds place, right? And we do 3 times 1 plus 2 times 10 plus 1 times 100. We add it together, 100 plus 20 plus 3, and we get 123. Fine. With binary, we do almost exactly the same thing, except what we do is rather than treating each position as a base of 10, as a thing of 10, we do it as of 2. Okay? So the first position is 1. Just like in decimal. The second position is not 10, but it's 2. The next position is 4. What would be the one after? Then? 512? 1024? Keep going? Very nice, okay. By the way, what's interesting is these numbers may sound familiar to you. When you're buying a computer and you look at how much memory it has, very often you'll notice these kinds of numbers. This is why, because you're storing data as binary, okay? Okay, so what value does this represent?
1.
Right, so 1 times 1 is 1, 0 times 2 is 0, 0 times 4 is 0, add them up, you get 1. Fine. 2, right, 1 times 2 gives you 2, and the rest are 0, so 2. That would be 3, right, just like in the lights. You understand why it's 4, it's 1 times 4 plus 0, so 4. 5, 6, 7. Got it? So this, what I showed you here, is exactly what I represented there with our transistors, with our lights. Yeah? Okay, now, we understand binary, this notion of using base 10 to represent numbers. Every one of those numbers, every one of those 0 or 1, is known as a binary digit. A short way of saying binary digit is bit. So if you're curious, if something is 10 bits, or 8 bits, or 16 bits, it just means it's that many of those numbers that can be represented. Got it? Okay, and a byte is nothing more than 8 bits. That's it. So if you ever hear something is whatever bytes, multiply it times 8, you get the number of bits. That's it. Simple, yes? Cool. Okay, so we talked about how we can represent numbers, and that's fine. But very often we want to represent text, right? You know, when you're writing, you're creating a document, like a text document, yeah, you might have some numbers in there, but you also have a lot of text. Well, how does a computer store that if it only knows how to store numbers, like, binary, right, 0 or 1? How does it store text? Well, it turns out there's a standard called ASCII, which basically says this. This number means this letter. It's a mapping, okay? Whenever you see this number, assume it's that letter. And so in this way, we can represent text. Let's look at an example. So this is just one part of the ASCII table of these mappings. I've just taken out the part that's A through Z, right? I omitted all the other stuff just for simplicity. Okay, so we can see here that the number 65 in this, according to this standard, would represent A, whereas the number 90 would represent Z. Okay? Well, if that's the case, hang on. Okay, suppose I have this binary number here. I've put in the positions for you to make it easier. So you just multiply them and add them together. What number do you get from this?
65.
Right, so it's 1 times 1, 1, right? 1 times 64, 64. Add them together, you get 65. What number is 65? A. Cool. Okay. What if you saw this number? What would this mean? U, right? You add 1 to 64, you get 65. Then you add that to 16, and you get 85. Right? U. Cool. What happens if you saw this number? A, U, A. Okay, anyway, you get the idea, right? So, so we can use numbers to represent text, just like we can store numbers to represent just regular numbers. With me? Okay. So, once we understand how to represent the problem, right? The next question is, how do we solve the problem? Well, in computer science, we have this term called algorithms, which sounds kind of scary, but it's not. All it means is a series of steps that take you from the problem to where you want to be, to the solution, sort of from the beginning to the end. Okay? So imagine this. You have as your input the information about the problem. Then you're going to have a series of steps that will eventually produce the solution at the other end. Okay? So let's look at a few. Let's imagine this very simple algorithm. Suppose I asked you, you need to get to class. How can you get to class? What are some ways you can get to class? And just from simplicity, let's assume you live on Komitas. Okay? Well, there are various ways you can get here from Komitas, right? One is you can walk. Okay? So you can imagine an algorithm like, you go down the elevator, you go down the stairs, you take a right, and then you take a left, let's say. You go down Komitas, eventually it kind of turns into Bahraman, you keep going until you get to the AUA stairs, you take a left, you go up the stairs, you get to the entrance, you go into the building, you go up the elevator, and let's just say you're in class already, okay? So that's one possible solution, a step-by-step solution, how an individual can get from home, from Komitas, to the class at AUA, right? So walking might be one mechanism. Another might be you take a bike. So again, you go down the elevator, you unlock your bike, you get on your bike, you ride down Komitas, you ride down Bahraman, you get to the stairs, you kind of walk up the stairs with your bike, or you could, I guess, take a left earlier and go down that other weird way. And then eventually you lock up your bike, you go into the building, you go up the stairs, and you're at your class, right? That's two possible algorithms. Another possible algorithm is you can take public transportation. So again, you go down the elevator, you go out the door, and you wait. And eventually, when the right bus or marshutka or whatever comes, you get in there, you go, when it gets to where AUA is, whatever, you pay the driver, you get out, you go up the stairs, into the building, up the stairs, pam, you're here. Last one is you could take a taxi. So you're at home, you click on the GG button or whatever, they come, you just go down the stairs, you get into the car, you say, take me to AUA please, and the driver just magically brings you here very quickly. You get out, you go into the building, and you're in class. We just talked about various algorithms, different kinds of steps that would bring to the same outcome, which is that you will eventually arrive in class at AUA. Question: which of these algorithms is the best algorithm? Taxi. Why?
Because it's the fastest.
Fastest. Good. Keep going. Yes?
It's expensive, the taxi. I will choose bike.
Bike is cheaper. Very good. Go.
Walking is free.
You can. I'm looking at you. Who you're thinking? Go ahead. I love how smart you guys are. Keep going.
It's the simplest way, taking a taxi.
Taxi is the simplest way, she says. Convenient. Taxi. Yes.
Depends on what we value more.
Depends on what you value more.
Your time or your money?
Time or money? Exactly. Okay, cool. All right, you guys are all over this. Very good. Okay, so look. It's difficult to say which is best because it depends. If you're late to class and what you really value is the time, you need to get to class fast, right? Otherwise, you're going to miss the test or something. In that case, time is really what you care about the most. And paying for a taxi, even though it's most expensive out of these, may actually be okay. You're willing to take that penalty because getting to class is so important to you. But at the same time, conversely, if you don't have to get to class that quickly, spending so much money may not make sense. Maybe taking maybe just a nice brisk walk if the weather's nice. Maybe you're worried about getting sick and you don't want to be out too much, but you don't want to spend too much money. You take public transportation. So I guess what I'm trying to say is, and most of you figured this out, it depends on what you value. It depends on context, okay? If what you care about is speed, taxi is, of course, the best way. If what you care about is saving money, walking is the cheapest possible thing, right? Even with a bike, you have to buy the bike, right? So walking is the cheapest thing, right? No, you have legs. Okay, so it really depends on context. With me? Cool. Okay, now let's consider another algorithm. Suppose I have a book. Here it is. It's kind of an old book, but there it is. And I want to find the word operation in this book. Okay? There are various ways I can go about doing this. One is this. I open up the first page and see that it's not there. I open up the second page. Not there. Next page. Nope. Not there. Okay. If the word started with Z, how long would it take me to get to the word? Suppose I had the time. How long? I mean, how many operations? Suppose that looking at each page is one step, one operation.
500?
Amount of the pages.
Exactly, the number of pages that I have, right? Okay, so if this page is, say, 1,000 pages, sorry, if this book is 1,000 pages, I would have to flip through 1,000 possible pages. And by the way, I may be trying to find a word that's not even in the dictionary. In which case, I go through the 1,000 pages and don't even find it. That's a bummer. Okay, so I could do something a bit more clever. I could maybe go 2 pages at a time. So, okay, it's not on the first page, so I skip 2. Not here, so I skip 2. Not there, so I skip 2. In that case, if the word is not there, how long will it take me? Exactly, half the time. Yeah, score. Is this algorithm correct? It depends, right? It might be correct, but it may not. Why? Exactly, I'm skipping pages. What happens if the word I'm looking for is between the 2 pages that I went through, right? Okay, so how could I adjust this algorithm to account for that?
To search with the...
You go to the, in the dictionary.
To start the letter that you're searching from.
Okay, so one thing I could do, you're right, so we know that it's ordered, exactly. So what I could do is, as I'm going 2 at a time, when I notice a letter that that's after the word, or not even the letter, just words where the letters are larger than the word I'm looking for, I can go back 1 page. Make sense? Okay, so the penalty there, if you think about it, is just the worst case is I skip and I go back 1 page. But the gain is that I've halved my problem. So is that a cost that I'm willing to take? Yeah, it's not that bad, right? Okay, so some of you might think, oh, well then why don't we make it 3 at a time? Or 10 at a time? Why don't we go 500 at a time? I think intuitively you understand that that's not a good idea either, because if you skip, you have to go back potentially that many pages, potentially 500, right? So you can't just keep increasing that forever. At some point, you have to stop. And as the problem grows, you're only limiting it by a small factor. So what can we do that's a bit smarter? Any suggestions?
You can open the middle page, see if the letter is before or after also.
Perfect. Exactly, yes, perfect. Okay, this is known as binary search. If you don't know what that is, don't worry. But notice binary, bi. Deciding between two things. Okay, hence the binary. So, okay, so I opened the book roughly in the middle. Okay, and I basically now have to just choose left side or right side. Whatever word I found, does that word come before or after the word operation? Now, if I open up the middle, I notice that operation comes after. So I forget about this half completely, and I focus only on this problem here. And I half that one. Okay? Now, again, I do the same thing. I decide, do I go left or do I go right? Okay? If the word is less than that, which it is, I go to the left, and I half that. Notice, at each operation, I'm halving the problem. Halving the number of pages. I'm eliminating half of the pages every time I do a step, right? Okay, so I keep sort of chopping things up, whatever, I keep, until eventually I get to it and I go, there it is. What would be the runtime for something like this? So think of it this way. If the first one, we had to go through each page at a time, and we had, let's say, n number of pages, n being some abstract variable, what would be the runtime, the worst case, for going through every page? N. The worst case of the original problem would be you have to go through the entire book, so n. N being the number of pages, n being the size of the problem. Yeah? In the second one, I have charts. Okay, wait. Okay, so in our first problem, where we were going one page at a time, our complexity of the problem, the time it takes to complete the problem in the worst case, grows linearly, right? Okay, if we do 2 pages at a time, we do a little bit better, right? We do it 2 times better. Not bad, but it's still growing upward. The bigger the problem, the higher it's going to go, right? With the binary search, with this idea of chopping it in half every time, we get logarithmic scale. Think of it this way. If I made that book 2 times thicker, and I was doing binary search, how many extra steps would I have to take before I find the solution? Exactly, just one. All I have to do is half it and throw the other half away, right? So why did we go through this exercise? There are algorithms that really depend on context, the ones that we discussed earlier, like getting to school, right? You have to understand what you value. There are trade-offs, right? There's cost against time, for example, right? The bigger the cost we noticed with taxi, the faster you get there, and vice versa if you walk, right? Okay, so we understand this. But then there are algorithms that are just better, like going to Sevan and coming to AUA from Komitas, or just coming to AUA from Komitas. Clearly, just coming here from Komitas is a faster, clearly a more optimal solution than going to Sevan and then coming back. You would agree. Okay, so some algorithms are just clearly better. And one of the ways that we can kind of figure out the runtime, like how many steps an algorithm has to take, is by doing this sort of thing, is figuring out its complexity, its runtime. How long would it take to do it? Okay, if you execute these steps, step by step, how long would it take to actually find the solution? Okay, and in this case, we found that doing binary search, using binary search, we've actually cut the problem down quite a bit. Okay. So, we're here. What are we going to be talking about? What is Intro to Computer Science? What are we going to be learning here? Well, we're going to begin with functional programming. Now, a lot of you have a background in programming. Okay, cool. Raise your hand if you know functional programming. By the way, don't raise your hand if you think functional programming just means using functions. It's not. If you know what functional programming is and you know functional programming, raise your hand. Interesting. 3 people. Okay, so this will hopefully be interesting to you. So we'll begin with functional programming, and the programming language that we'll be using is JavaScript. One important note. This class is not about learning JavaScript. Actually, this class is not about learning programming. It's not about learning algorithms. It's not about learning cryptography. It's about building up the intuitions and the necessary skills and gaining algorithmic thinking to begin to understand how to solve problems. Programming, whether it's JavaScript or Java or algorithms and understanding cryptography and so on, these are all tools that will provide you with the necessary skills to solve these problems. The goal is problem solving. It's not learning how to type, okay? Okay, back to what I was saying with JavaScript. We will not be learning JavaScript. By that, I mean the goal is not to learn the syntax or the language of JavaScript. The goal is to use the parts of JavaScript that will help us understand programming concepts. So we're not going to learn everything about JavaScript, just the parts that I think are important to understand functional programming and understand sort of what cycles are, what recursion is. We can do a lot of debugging, functions, etc., etc. Okay? Once we've done this, the next programming language we will learn is Java. The two sound similar but are completely different. They are 2 completely different languages. We will first learn JavaScript, then we will learn Java. Why do I want you to learn Java? Well, first, it's always better to learn another programming language, right? The more you know, the better. But second is because moving forward, many of your courses, like object-oriented programming and data structures, will require you to know Java and possibly C++, but if you know Java and you understand it well, C++ you'll be able to pick up fairly quickly. So that's why. So we'll start off with JavaScript, get good at programming, then move on to Java, okay? As far as concepts, we'll be learning functional programming, we'll cover some basic object orientation, we'll also study a bit of cryptography, we'll look at some algorithms, we'll do some web development, we'll do graphics with Canvas, we'll do we'll do a lot of really cool stuff. Okay, I'm more excited than you, I think. By the way, this is scary. Have you ever had a teacher who's excited to teach? That's like the worst thing you can have. That means you just, okay, no, it's good, yay, no. Okay, listen. So I'm going to assume, even though many of you raised your hand when I asked if you have programming background, I'm going to assume that you know nothing about programming, okay? We're going to start from 0. And those of you who think you know programming, I'm going to reteach you how to program with functional programming. For example, those of you, raise your hand if you think you know JavaScript. Oh, okay, I was expecting more. Oh, okay, all right. So for those of you who use JavaScript, maybe many of you use var, for example. We're not going to use var. No more var. Even let, for the first, it's just going to be const everywhere. No mutation. It's going to be hell, but it's going to be fun. Like I said, I'm not going to assume that you have any programming background. So I will touch on every detail one at a time, but we are going to go fast. Okay? So those of you who have the programming background, you won't get bored because we are moving very quickly. But for those of you who don't have a programming background, don't worry because we are going to cover every detail. Okay? A bit about the culture of the class. Yeah, right? I know. Some of the, yeah, from previous year. So this is a picture from last year, a photo from last year. This is office hours. This is what office hours looks like. Lots of people excited to code, worried about exams, but they're still there, figuring stuff out, building cool stuff. This is what it's about, okay? One of the things I want to make sure that you guys understand is grades don't matter. And I keep saying this, and it seems like many of you don't believe me, but I'm serious. When you go to an interview, no one's going to ask you, what did you get in Ruben Meschan's Introduction to Computer? Like, no one cares. What they care about is if you know your stuff. Can you bring value to the company? One way to think about it is imagine yourself as an employee. Imagine you want to build a software company. You want to build the next Facebook. Who would you hire? Right? In the interview, would you say, so did you go to AUA? What are your grades? No. What would you ask? Well, what have you done? What have you built? Right? You look at what they've done because that's kind of shows what they can do in the future. You give them programming tests, right? You do code readings. You have them work with you for a while and see how they work and the kind of code they write and how many mistakes they make and so on. And that's what you care about, not the grade. And so the one thing I want to make sure that all of you do is, regardless of how easy or difficult you think the class is, don't focus on grades. Don't focus on like, I really care about my quiz. Learn the material. I guarantee you that if you focus on learning the material, you will get a good grade. Okay? You will. Okay, I can't guarantee you, but I really can't, right? It's pure math, yeah. But I think you will. And judging from last year, it worked out very well, right? Even those who thought, oh my God, I'm failing. I got a 0 on my first assignment. Oh my God, and then they got an A at the end. So don't worry. The second thing is, so there's a lot of material online, okay? Use it. Watch YouTube videos and tutorials and so on. It's important to learn from other people's knowledge, right? But again, as part of our culture, it's important that we're not only consumers of information and knowledge, but we're also producers. Which is why, in almost every homework assignment, except the first one, everything that you do, all the code that you write, is going to be free and open source for everyone to see. Okay? So all the code that you write, all the assignments that you do, will go on GitHub, I'll tell you what that is later, and will be available for everyone. Everything we do here is open source. The second thing is you will be helping teach others. What do I mean by this? You will notice that I am being recorded. There's a reason for this, because if you've missed something in class, you can just go home and watch on YouTube, because all of my lectures will be available for you to watch on YouTube. In the same way that I'm sharing my knowledge with you, I expect you to share your knowledge with others. You will do this both when you work in groups, helping each other, etc., but also through something very simple. You will be making YouTube tutorials. I found that there are two ways to really understand if someone knows something. Okay? One is just have them build it. Right? If you can build a computer, you probably understand computers. Fair, right? Okay. Another way, though, is to try to have them explain it to somebody else. If you can explain a topic well, you probably understand it. If you can't, if your words start getting fuzzy and people are like, wait, what you just said didn't make sense with the other thing, it's clear that you didn't understand the topic. By the way, one way to know if a professor knows what they're talking about is exactly that. If you can't understand what the professor is saying, they probably don't know what they're talking about. Okay, so what you will do is make these tutorials and make them public. So we will watch these tutorials and grade them and so on, but others can then use these tutorials to learn the content that you are teaching. So that would be pretty cool. You can turn comments off if you want or leave them on. That's but the videos have to be public. Okay? By the way, that causes stress to a lot of people, which is a good thing. Stress is good, by the way. Stress will keep you focused. You have to really pay attention to what you're saying when the entire world is watching you. Don't say stupid things. So that means you have to work harder to build good videos, right? You have to really watch what you're saying. That's a good thing. That will force you to learn the material, which is exactly why we're here. Okay. So as far as materials go, there's no book that you have to go and buy or whatever. All the content that you will see in your exams or whatever, your homework assignments, whatever, it's all based on, mainly, for almost 99% of it, is based on what we discussed during lectures. Okay? And you have the YouTube video, so if you feel like you've missed something because you weren't able to take a note or whatever, or you were sick that day, you have the YouTube videos to watch, right? So you're not going to miss anything. If there's a topic that I discussed that you don't understand, there are various resources that you have at your disposal. One is you can just Google the topic. Seriously, if you don't understand functional programming, Google functional programming. If you don't understand recursion, Google recursion. And then read the articles, read the tutorials, and that will help you understand it. There's some fantastic tutorials, some of them made by the way, students from the previous year, some of which will be made by you in the future, on YouTube. Use them, okay? They will help you become better programmers. And again, everything that those students did is also open source and available for you to read. Okay, at the end of the semester, there's a thing that we call the CS110 Expo. This is a picture from last year. Here's a team. This is the Lemon team. Anna, Jan, that's the Lemon team. What is the Expo? So at the end, you have to do projects, right? Which we'll talk about what percentage that counts for, blah, blah, blah. It's a team effort, and your job will be to build a project that people want to use. So it can be a game, it can be a tool, it can be whatever, right? And at the expo, you have a booth where you present your project, right? So we get lots of people from industry coming, possibly looking for potential interns. Lots of networking happens here. And you really want to make a booth that shines, that people notice, right? So you want to have a great project, great presentation. As you can see, in fact, the Lemon Group, they did something really cool. They had these lemons, and they had a game, and everyone who won the game would get a lemon. Just amazing. Anyway, great team, great presentation, one of the best. So something to look forward to is the expo at the end. You can invite your friends, your parents, and so on. They'll come and be wowed by all the code that you wrote. Okay. So that's that. What time is it? Ah, okay. Okay, as far as resources, I mentioned Google. If you don't know something, Google it. There's Code Academy. Actually, your first homework is going to be on Code Academy. It's on Moodle. Just go and read it. Yeah, I'll say, okay. YouTube is there. Again, go watch tutorials, learn by yourself. Okay, the team. Can the team please come up here? Come on, come on, come on, come on, come on. Woo! So your TAs, so when Google fails and YouTube fails and you're stuck and you're crying at night and you don't know what to do, these are your saviors. These are your my teaching assistant, your TAs. Naira, Vazgen, and David. They're awesome, they're smart, they're kind. They will be your guides. They are there to help you, to guide you. They're awesome. You guys are really lucky to have this team. We were actually together for 2 months before the course, just preparing the course for 2 months. So everything that you see, all the lectures and everything, actually these pictures, that's David's work. We have some really interesting things ready for you guys, so I think you'll be pleased. Thank you so much, guys. Give them a hand, come on. Okay, so some just basic details about the class that everyone is going to be asking. So let's go through the syllabus very quickly. This is my least favorite part of the lecture, but whatever. Okay. Oh, we have a Facebook group. Okay, if you search for CS110 Fall 2017 Introduction to Computer Science, you will find it. That's a link. If you have phones, you can just do it now. You have to request to get added. We add you. It's important that you become part of this group because a lot of the things that we share through the Facebook group, okay? So make sure you become part of this group. Moodle we're basically only using Moodle for like grades and homework, but almost everything else, it's Facebook group, right? Videos are shared through there and yeah, just get on that group. Okay, I talked about the teaching assistants. Office hours. We have 4 different office hours. Here they are. Okay, that's it. By the way, there's a link to the syllabus from the Facebook group. So once you get into the group, you can get access to the syllabus. You just click on the link and it takes you here, okay? Let's see, the Moodle key. Everyone seems to want to know the Moodle key. Here you go, there it is. Okay, required materials. 2 things you need. Okay? You need access to a computer so you can do your homework. I think that's fair. You need to program, so you need a computer. It doesn't have to be an amazing computer, just one with like text editing. Fine. The second thing you need is some sort of a digital video recorder. It can be your phone, it can be the camcorder on your computer. Doesn't matter, but just some way that you can record yourself so you can do your tutorials, your YouTube videos, okay? Oh, one small thing, your face has to be in the video. And it has to be your voice too. Okay, all right. Okay, method of evaluate. Okay, this stuff some of you care about, so just pay attention to this. So problem sets are accounting for a lot, right? They're 45%. I dropped the lowest grade, okay? So you get a whole bunch of, you're gonna get a problem set roughly every week, one per week, roughly. You know, sometimes it might change, especially when you guys come crying, oh, we have midterms, okay, I'll see what I can do. But generally about once a week. We dropped the lowest one. Be careful. I purposely mess around with the due date. Like the due date, I think for this one is at 11:45 or something. Make sure you're not late. And by the way, the people from last year will tell you, if you're even a second late, I'm serious, 1 second. What do you mean a second? No, seriously, 1 second late, it's a 0. I will not accept it. Do not be late. Do not say my clock is different from your clock, and if that's submitted 1 hour earlier, then that will not be a problem, right? But I lost internet, I'm at my house. Why were you waiting for last minute? You know you live in Armenia, sometimes you lose internet. Run to a cafe, get it done. If you can't get it done, it's a 0, I don't care. Deadlines are deadlines. Do not be late, okay. Quizzes. So there are no exams. No finals, no midterms, none of that crap, don't worry. But we have quizzes. But here's the thing. I'm not going to tell you when, and I'm not going to tell you what. Wait, huh? I'm not going to tell you what the quiz is going to be about, so you can't study for it. And I'm not going to tell you when it's going to happen for you to know to come to class. If you're here, great. If you're not, 0. I dropped the lowest one. So if you're sick or whatever, you happen to miss the day when we have the quiz, don't worry. It's not going to count. 1 is okay. There are no makeups. There are no late policies, whatever. If you're not here, it's your problem. I don't care. There are too many of you. But remember, I dropped the lowest one. So save that one for a real emergency. Don't just say, I don't feel like doing this one. And he drops it in. Yeah, but one day you might not be here, or you're late, or whatever. Save it. Trust me. Okay? Don't waste your lowest grade. And at the end, we have the projects, which we then present at the expo, at the CS110 expo. So that's going to be fun. Okay, I'm going to say this one more time just to make sure everyone's on the same page. There is no late policy. Late means 0. There's no late policy. And late is anything beyond what the Moodle deadline is. That's what it is. Whatever Moodle says, that's it. If you go 1 second late, it's your problem. Policy on grade appeal, if you want to come whining to me, go ahead. Makeup procedures, no makeups. Remember, I dropped the lowest grade in quizzes. I dropped the lowest grade in problem sets. Fair? Good. Okay. Wait. Where are we? Ah, here. By the way, this is what the Facebook group looks like. It's very fancy. Here you go. You can see the syllabus link is here, so you can click on it and read all that stuff I just showed you at your leisure. Yeah, I should also note that your homework 1 is available. Basically, I want you to learn CSS and HTML. I'm not going to teach it. It's too simple. Just go to Code Academy, learn it yourself, send me the link saying I know it, and done. Okay? Okay. But know it. I'm serious, because the next homework, I'm going to assume you know HTML and CSS. So actually do this. This is important. Don't waste your lowest grade on this. Okay, we got the syllabus. Facebook group, that's it. So you just search for CS110, fall 2007, Introduction to Computer Science, boom. Welcome to the class. So we have about, what, 15 minutes? Does anyone have any questions? Yes?
How the quizzes are going to be? Like, if we are going to write code on a piece of paper?
Yeah. Next question. Okay, so the question was, are we going to be writing code on a piece of paper? Yes. If you know how to write code, you can write code on sand. It doesn't matter what the medium is, right? You're just writing code. So it's a good idea that you bring pencils with you that have erasers so that it's not a mess. Last year, we had some students that purposely, I'm pretty sure purposely, wrote code that was impossible to read, thinking that we're, you know what I mean? Like, we're going to magically see the right answer in that crap that they made. No. We were students too. We're not that old. We know the tricks. Don't do it. Write good, clean code or you get a 0. Next question. No questions. All right. I won't waste your time. Thank you so much. I'll see you guys day after tomorrow. Cheers. Kevin! Hey!